Hey guys, I'm Jack. Welcome back to my LeetCode Review One Take blog on 127th problem, word ladder. A transformation sequence from word begin word to word end word using a dictionary word list is a sequence of words from begin word to S1 to S2 until Sk, such that every adjacent pair of words differs by a single letter. Every Si, where I is from 1 to K, is in the word list. We have to note that begin word does not need to be in the word list. Sk equals end word. We are given two words, begin word and end word. And the dictionary word list, we need to return the number of words in the shortest transformation sequence from begin word to end word, or 0 if no such sequence exists. And let's see example 1 here. We got the begin word heat and end word cock. One shortest transformation sequence is heat to hot to dot and cock, which is 5 words long. So our output is 5. Then let's get into our intuition solving this problem. When we look at this problem, we may immediately recognize it as a graph traversal problem. Each word can be seen as a node in a graph, and there's an edge between two words if they differ by exactly one letter. This question is asking us for the shortest path from begin word to the end word. And let's walk through a few approaches to solve this problem. And the first method that could immediately come into my mind is the brute force depth first search. We can track all possible paths use depth first search, but this method would be very inefficient for finding the shortest path. Or we can use the breadth first search to explore all possible word transformations level by level. And the third approach, called bi-directional breadth first search. This method would search from both begin word and end word simultaneously to potentially reduce the search space. And let's start by implementing the standard breadth first search at first, because it is the foundation. Well, the core idea of the breadth first search is we have to perform a level order traversal starting from the begin word. We'll use a queue to keep track of words to visit, and a set to store visited words to prevent cycles. Then we generate all the possible one-letter mutations and see if any of them exist in a dictionary until the end word. First, we convert the word list into a hash set for big O of 1 lookups, which will make it more efficient to check if a word exists in our dictionary or not. So we create a set of string called word set gets a new hash set, and input parameter is word list. Next, we need to check if the end word is in a dictionary. If not, we just return 0 immediately because it is impossible to reach. If not single word set that contains end words, If so, we'll return 0. Then we'll initialize our breadth first search queue with the begin word. Queue of string. Called, let's say, queue gets new linked list. And we'll start the search from the begin word. So we'll add it into the queue. Queue.offer of begin word. Following that, we need to keep track of words we've already visited to avoid cycles. So the code is set of string called visited gets new hash set. And we'll mark the begin word as visited. Visited dot add of begin words. Next, we'll declare a variable to check the number of transformations. So we'll start with a length of 1 for the begin word itself. Integer level started at 1. Now we have to begin our breadth first search with a while loop. And this loop will continue as long as there are words left to explore in a queue. While not logical symbol, queue dot is empty. For each iteration inside while loop, first we'll grab the size of the queue here. This represents all the nodes at the current level. Integer size gets queue.size. Then we'll process all the nodes at the current level before moving to the next. We'll create an inner for loop, integer I, started at 1. When I is less than size, we'll increment I after each iteration. Inside the inner for loop, first we'll get the current word we are examining. String current word gets queue.call. Next, we have to check if we reached our target word. If so, we just return the current level as we have found the shortest path. If current word equals of end word. If so, we'll return the current level. Otherwise, we'll try to change each character of the word to find their neighbors by transforming the current word to character arrays at first. So we need to declare a variable called word characters, and the type is character array. Word characters gets current word to character array. Then we'll use a for loop to iterate all characters in the current word. For integer j, started at 0, and when j is less than word characters dot length, we'll increment j, oops, after each iteration. For each iteration in this for loop, at first we need to save the original character so we can restore it later. Character original character gets word characters of j. Oops. Now we need to create an enhanced for loop to check each possible letter from A to Z at the current position. For character C starting at A, when C is less than or equal to character Z, will increment C after each iteration. For each possible letter, we'll skip it if it is the same letter as the original character. If C equals original character, then we'll continue the loop. Otherwise, we'll replace the character and create a new word. Word characters of J gets C. And we'll create a new word. String new word gets new string of word characters. After that, we'll check if the word is in a dictionary and hasn't been visited. So the code is if word set that contains of new word and not symbol with visited that contains of new word. If so, we add it into our queue for further exploration. Queue.offer of new word. And we'll mark it as visited to avoid processing again. Visit.add of new word. Out of the for loop, we need to restore the original character for the next iteration. Word characters of J gets original character. After processing all words at the current level, we'll increment the level to reflect the increased distance from the start. So we'll increment the level. Finally, when the queue becomes empty and we never reach the end word inside the while loop, it means there is no transformation sequence exists. So we'll return 0. Alright, that's all of the code. Let's submit our code and check if our solution passes all the test cases. And bravo, our code got accepted. Now, let's analyze the time and space complexity. For the time and space complexity, let's declare that N is the number of words in the word list, and L would be the length of the words. Inside the breadth-first search loop, in the worst case, we'll visit every word for one time, and for each word, we iterate through its L positions. For each position, we also check 26 letters. And inside this loop, we create a new string and check for its existence in the hard set. Both take big O of L time. So processing one word is L is L times L times, let's say, 26 times L. So the total time complexity is dominated by the breadth-first search, which is L times 26 times L times N. And for space complexity, first, the word set and weighted set can store up to n words, each of length L, leading to the big O of n times L. And for the Q, in the worst case, could also hold a large number of words, which is also big O of n times L space. So the overall space complexity, it is n times L. And this is the end of my LeetCode review blog on the word ladder problem. And I highly recommend you guys to visit my online GitHub page on this website. You can see all the problem description, intuition ideas, and each solutions with very detailed comments and the final time and space complexity. Furthermore, we can also see the bi-directional breadth-first search method here with detailed code, comments, and time and space complex analysis. We can also visit my GitHub repository here, which contains all the codes and notes to build this online GitHub page. And I'll put those two links on my YouTube description below. And thank you guys for watching. I'll see you next time. Bye bye.